mini video lectures. We'll just talk about some properties of matrices, and we're going to introduce the idea of matrix inverse. There's a whole theory and could be a whole chapter on matrix inversion and its relationship to other mapping properties of linear transformations, and we are going to hold off on that until we get back from break, but I wanted to give you enough the mechanics to get started. So before we do that, let's just talk about sort of mechanical and algebraic properties of matrix multiplication. In the previous lecture, we talked about arithmetic with matrices, and I talked about theorem 1. Nothing sort of out of the ordinary there, but with matrix multiplication, we have to be careful. As we already said, I'll drop down here first. In general, AB does not equal BA. So even if both of these are defined, which in general would only be the case if so there are lots of situations. So if A is 2 by 3 and B is 3 by 2, you can change their order and you can perform the multiplication, but you're not guaranteed that they'll be equal. And in full generality, it's not the case that A and B can even be multiplied in both of these ways. Usually, if it can be multiplied A and B, then it's likely that it can't be multiplied B times A. So the point is, just remember, in general, AB does not equal BA. Matrix multiplication is not commutative, even when the matrices are square. And maybe we'll just skip down here to look at this example. So here's two matrices, A and B. And assuming that I did my multiplication right, A times B, right, and the way I think about mechanically doing matrix multiplication is row dotted with column. So the first row dotted with the first column gives me entry here. So 0 times 1 and 1 times 0, that's 0. 1 times 1, 0 times 0, that's 1. So to go over here, we do first row, second column, 0 times 0, 1 times 1, that puts a 1 there. Second row, second column, 1, 0, 1, 1 is 1. And so you notice here that this is the matrix product A times B. But if I just switch them and I put B over here and I put A over here and I repeat those steps, I get a matrix which is not the same. So this is a situation where A and B can be multiplied in either order, but when you do it, you get two different results, demonstrating the lack of commutativity. Other properties. So this is associativity of matrix multiplication. This is true. So based on what we talked about before, which is essentially that when you multiply matrices, you're composing linear transformations. Composition is associative. So you can multiply B and C first and then multiply the result times A. Or you can multiply A and B first and then multiply the result times C. So either of those yields the same outcome, which means we can write ABC and you can compute it in either of those two ways. In terms of matrix multiplication being linear, you have to be careful here because we've talked about the fact that linearity has different meanings in different contexts. So really what we mean is matrix multiplication in this context distributes. So there's a disclaimer here that A, B, and C all have to be matrices such that these actions are defined, meaning that their respective dimensions match. So here, B plus C, in order for that to be defined, B and C have to be the same size matrices. And in order to be able to multiply from the left by A, if this is an M by N matrix, then this needs to be an N by something matrix so that this multiplication makes sense. But if it does, then everything works out nicely, and you can distribute A through this sum and also through constants, which is what happens down here. You can combine these two rules if you want, and that would give you the sort of linear rule that we're used to, which would be A times RB plus SC, and you can distribute through sums and through constant multiplication. You can also do right distribution. So right distribution here means that this would be C times A and this would be B times A. So notice though, it is important to keep A on the right hand side of C and B over here. Oh, this is wrong. I'm so sorry. This should be C times A. This is a mistake here. I apologize. This should be B times A plus C times A over here. I apologize about that. But again, since in general A and B and A are not the same thing, you have to keep A on the right-hand side. You cannot swoop it to the left because that would imply that B and A commute, which, as we said, in general, they do not. This is just a property of the identity. So if you have a matrix A, which is M by N, and you put the M by M identity on the left-hand side, well, that makes sense because if A is M by N and this is the M by M identity, then this multiplication makes sense. But multiplication by the identity does nothing. That just produces A, and you can check that. And if you put it on the right-hand side, it needs to have the right dimension, so that would be N by N. And again, if you multiply A on the left against the identity, you'll also just get A. So those are the algebraic facts for matrix multiplication. So another operation that's useful is called transposition, and this is an easy one. Transposition just swaps rows and columns. So the way to really think about this is in terms of entries. So the matrix is composed of I and j entries. This tells you what row you're in, this tells you what column you're in. So the transpose of a given matrix just takes the entries and swaps them. So the I goes to the j and the j goes to the I. And there's a couple ways you can visualize this. So I said before, you can swap columns and rows. That's one way to visualize it. The other way you can do is you can sort of flip or flop over the diagonal. And so just quickly, if you look up here, if A is an m by n matrix, then A transpose is an n by m matrix because the rows have become the columns and vice versa. So there were n columns before, and now there are n rows. So just by way of example, so here's a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's the diagonal, 1, 5, 9. So we're going to flip over this diagonal. And since this is a square matrix, namely 3 by 3, the transpose will also be a 3 by 3 matrix. Transposition fixes the diagonal. That's what this says. So the diagonal doesn't go anywhere. The reason for that is if you swap I and j, whenever I and j are already equal, namely the 1, 1 entry, the 2, 2 entry, 1, 1 entry, 2, 2 entry, 3, 3 entry, when you swap the 1 and the 1, you just get 1, 1. And when you swap the 2 and the 2, you just get 2, 2. And when you swap the 3 and the 3, you just get 3, 3. So these entries stay fixed, but you'll notice that this 4 goes up here and this 2 comes down here. This 7 goes up here, this 3 comes down here, 6 and 8, and 6 and 8, and 9 stays. So this is A transpose. So you can think of this as an action. You had a matrix, you transposed it, and after transposing it, this was the resulting matrix. And if you want, just again, the first column is now the first row, the first column here is now the first row. You can transpose matrices that aren't square. So here, the diagonal is here, so you flop over the diagonal. This will go here, this will go here. First row becomes first column, second row becomes second column. And again, the diagonal is fixed. There are some rules with transpositions, so let's just work them out. If you transpose and transpose, you're flopping over the diagonal twice. That results in the original matrix. If you add and then flop, or flop and then add, it's all the same because addition works component-wise. The only one that takes some thinking is AB as a product transpose. AB product transpose is B transpose times A transpose. And this is called the socks and shoes rule because if you put on your socks and then your shoes, when you take them off, right, you have to take off your shoes first before your socks. That's how I learned it. It's a little bit silly. The best way to think about this is that if you think about dimensions for A and B, and you do this product, and then you transpose, in order to make the dimensions work out, you have to do the multiplication in this way. Otherwise, you'll end up with objects that can't be multiplied. So that's why I put the word why here, because I want you to actually think about why this is true. And you can test it or look at examples in the book, which sort of go through that. A couple other quick facts. The dot product, as we defined before, v dot w, you can actually now define this in terms of matrix multiplication. So if you give me two vectors of the same size, so I wrote here v and w are in Rn, namely they are n by 1 matrices, right? N rows, 1 column, they're vertical, regular matrices. When we dotted them, we know that we get a scalar, but one way that you can actually see that through matrix multiplication is you can define the dot product as being this matrix multiplication. And so again, if v and w are both length n vectors, then V transpose is now a row vector, which has 1 row and n columns, and W has n rows and 1 column, and that makes this multiplication valid. So look, if you look down here, V transpose is now 1 by n, W is n by 1, so that means that when you multiply 1 by n times n by 1, the result is a 1 by 1 matrix, which is just a scalar. So this is a proper definition of the dot product. And if you want to think of it like that, you can. This will be useful later on. When A is square, you can multiply, so if it's n by n, then you can multiply A times A. This dot shouldn't be there. It's misleading because it's not the same as this dot. I'm just saying if I write A next to A, then that's a matrix product. We know how to multiply matrices. But in this case, we can just write A squared, and we know that we mean A times A, or the composition of the linear transformation given by A with itself. And of course, you can do this as many times as you want, as long as it's a square matrix. And just as an aside, this will come up later, if you can multiply a matrix as many times as you want by itself, that'll give you this notion of a to the k. That means you can actually define things, for instance, like the matrix exponential. Or you could, for instance, define sine of a or cosine of a using this power series representation. Because e to the x is none other than x to the n over n factorial. So e to the a is none other than the a to the jth power over j factorial summed as j goes from 0 to infinity. And one can show that this series converges, and what it converges to is indeed a matrix, and that matrix is called e to the a. Okay, lastly, we'll do this quick. I want to talk about formal invertibility, but with no deep theory. Although it seems like we're kind of making a hard left and detouring, we're going to come back to another operation that involves matrix multiplication, which is matrix inversion. So this whole story about linear algebra is that we're interested in solvability, and in particular unique solvability. So when do we have a solution, and when is that solution unique to this linear system ax equals b? So if we're thinking about a linear transformation, A is transforming the vector x into the vector b. But when we're thinking about solvability, I'm giving you b, and I'm looking for the solution x. And if this were just a good old-fashioned algebra equation from high school, we all know that to solve ax equals b, you just divide by a. Well, when a is a scalar, as long as a isn't 0, life is good. But if a is a matrix, division by a is not well defined. However, this matrix inverse is an object that will exist under certain circumstances. So what this says down here is if we're thinking about a as a linear transformation that maps a given x into a b, which is what this says, then we're also asking about another linear transformation, which is the inverse of that operation, namely the mapping that takes for each b in Rm back to the solution x, which has to be unique if this mapping is well defined, and that mapping goes from b to x. So if a goes from x to b, where ax equals b, then we're going to define a mapping which is a inverse b, which takes you from b to x. So mapping a inverse takes you from b to x. In order for this notion to make sense, it will turn out that the matrix needs to be square. And in particular, the square matrix will have to be both one-to-one and onto, or injective and surjective. More on that later, and we already sort of have the theorems we need in order to see that. But for now, we'll just take as given that the matrix needs to be square. That's the first thing in order to have this inverse operation defined. And the matrix we are trying to invert has to be both injective and surjective, or one-to-one and onto. So if we're in the situation where A is an n by n square matrix, and let's say that it has those properties so that A inverse is defined, we're going to write A inverse as A to the minus 1. And if you want, you can think about this as sort of division by A when it makes sense. But really what we're doing is we're computing a new matrix, A inverse, which is exactly this mapping that takes you from B to X. So it's the solver for this equation. If A is the thing which takes you from X to B, what we're looking for is the matrix that takes you from B to X. And you'll see down here, that's exactly what at the very end we're going to have is this new matrix A inverse. So if A is a square matrix and A inverse is defined, this will be a square matrix. And that matrix can be applied to B to yield the solution X. So AX equals B will be equivalent to X equals A inverse B. So there are a few other things to say here. A inverse is this object, which will be another square matrix. And so if you just start here, you can formally do the algebraic steps, which you've been doing things like this your whole mathematical life. If you start with AX equals B and you apply A inverse to both sides on the left, A inverse, if you knew that this was true to begin with, okay, then you apply A inverse. A inverse undoes the effect of A. So A inverse times A will result in the identity, the n by n identity, because if you do A and then undo A, you've done nothing, and the map which does nothing, or the transformation which does nothing, is the identity. And I just wrote here this little fact, A inverse times A equals A times A inverse, which is the n by n identity. When you apply the identity to X, you just get X, and so by applying A inverse B on the right-hand side, you've just derived this property. So the point is, if you know that A inverse exists, or if somebody gives you the object A inverse, you can use it in this very nice way. But the big questions that we have yet to answer up to this point are, when does A inverse exist? And we've already sort of said we need a square matrix, and we need that linear transformation to be 1-to-1 and onto. But we need some better criteria to check whether or not the inverse exists, and we will have that. And moreover, if it exists, we need to know how to find A inverse, which means algorithmically, how do we produce it? And we could actually ask these questions in reverse order. We could introduce the algorithm, and we could simply declare whenever the algorithm works, A inverse is well defined, and when the algorithm fails, then A inverse does not exist. So more to come on that later.